9:05, so let's get to it. Where's Monsieur Trap? I miss your trap today. All right, so we're going to start some new stuff today, um, namely sequences and eventually series. So series is what we'll get into next week. Um, Also, I guess just a couple of quick business announcements. So there was a collective freakout moment on Wednesday because you all thought you were failing. Are you all failing? No, you're not. Mr. Trap is. You're failing. And you also have wet hair. Very wet, unruly hair. Um, so, um, yes, I do. Um, no, so I was just talking about how there was a collective class freakout on Wednesday because you all thought you were failing. And you know what you guys are not all doing? Failing. Huh? Yeah. So the spreadsheet, right, thing that Dr. Insaldi sent to each of you just shows you which things you've passed, which things you haven't, and then periodically we update as we grade the tasks and also the infinity. Okay, there was a key line though. It says if you do nothing between here and the end of the semester, then your grade will be. And not shockingly, if all of you guys just basically say, you know what, until November, I'm not doing any more calculus for the rest of the semester. What grade do you think you would earn? Probably an F, right? Because we're not even halfway through this. We're almost halfway. But okay, so don't freak out about those spreadsheets, right? Um, they're just there to show you which things you've done and not done, right? Okay. All right. So the other thing to mention is right. So Monday we'll have our next fluency assessment. It'll be fun and exciting. And it will not have the sequence stuff that we're going to do on here, so don't worry about that. Let's see, um, and like last time, you'll only get problems that you actually haven't mastered yet. So um, yeah. Anyway, well, as opposed to me just giving you everything, right? Even if you, yeah. So now that said, we can post on Canvas because this would be perhaps useful for review and study purposes. Um, the all of the questions, not just the ones that Jack or you or whoever has to do, because then you can see more problems over things. But anyway, um, okay. So yeah, so don't freak out. Everything's fine. Uh, Now, since most of you are freshmen, uh, in uh, actually all of you are freshmen, right? Yeah, you're all freshmen. Um, so not next week, but early the week after, we have to submit midterm grades to the registrar, and you guys will see those midweek. And so basically, what Dr. Insaldi and I are going to do is we're going to sit down and say, okay, let's pretend that the semester was over right now. What grades would we give everybody, right? And those don't go on your transcript. They're purely for advisory purposes, right? So you don't, you'll see them, your advisor will see them, and they're just meant to be exactly that, advisory as to, how are you doing, okay? All right, so sequences. So the idea of a sequence is basically just, it's a function that instead of taking any value as input, we only allow it to take the whole numbers as inputs. Okay. And depending on how you feel in the morning, you can either start with 0 or 1 as your first value of the input. And there's good reasons to do it both ways. Okay. So some just examples would be, if I had something like this, what would be the first value? And then it's just a function. It's just that, right? So in terms of plugging in values or anything, um, you just do like you do with any function, except I'm only letting you plug in whole numbers. Okay, call question.
What's the context of this? Where did this, what is this used for?
Oh, the sequences stuff. We'll see a lot more of that.
This is like a totally new concept.
Yeah, we're completely like right. So chapter 7 was all about applications of integration to various things, right? So areas, volumes, surface area, arc length, all that kind of stuff. And we're starting chapter 8, which is all about infinite sequences and series. So in the language of Monty Python, this is and now for something completely different. Um, yeah.
I haven't seen the movie, but I like the.
Well, okay, yeah. It's more funny. That one's not from Holy Grail. It's from the and now for something completely different is from Meaning of Life, I think, or maybe it's Flying Sir. One of them, not Holy Grail. It's from a different one. Okay. Um. Anyway, so a sub 2 in this case would be 2 over 2 plus 1, which would be 2/5, and a sub 3 would be 3 over 3 plus 1, which would be 3/7. Uh, yes, because 2 plus 1 is 3, not 5. And 3 plus 1 is 4. Okay, well, it's a good thing it's Friday. It is definitely one of those days. Because I was like all kinds of backwards with the recursion this morning in computer science.
Forget everything I just told you. It's a good thing it's Friday.
Yeah. Well, so we were doing the Towers of Hanoi and recursion in computer science right before this, and you have to choose an ordering scheme. So last time on Wednesday, we chose one ordering scheme. And then I realized actually that was probably not the ordering scheme I wanted for reasons. So I said, okay, let's redo it. Let's change the ordering scheme to this so that we can do this new thing. And that new thing actually used the same ordering scheme from the first ordering scheme. So I was all kinds of jumbled up. And you guys are probably all super confused. Okay, anyway, so right, that's it. The sequence, I just plug in values and I get whatever I get. And now, what do we think we could probably care about? Well, like with functions, we want to know what's the limit of these things, right? So, question. What's the limit as n goes to infinity of one of these dudes, right? So we're interested in the in behavior of these sequences. Now, what tools, if I were dealing with a function like f of x, what tools do we have to determine the value of limits? Okay, graphs would be at least a way to kind of an intuitional approach. But yeah, we could certainly graph things. Uh, we also have L'Hopital's rule. Okay. We also have, well, the squeeze theorem. How many of you guys were like, oh, right, that, after the last fluency assessment? You forgot about the squeeze theorem from Calc 1? Yeah? Did you not learn the squeeze theorem in Calc 1?
No, I remembered it.
Oh, okay. Yay. It wasn't a trap.
Right.
Right. Oh, that's right. I remember this. Okay. So, all of the same rules that we have on the table apply to uh, apply in almost all situations to when we're dealing with sequences. And I say almost all because there are a few funny situations, but I'll talk about that in a minute. Okay, so for this particular example, what do you think the limit is? There's a couple ways we could see this, right? If we just looked at the values, 1/2, 2/3, 3/4, 4/5, and so on, what do you think that's converging to? 1, okay? And does it make sense from, say, L'Hopital's rule that it is in fact 1? Because what's the derivative of n? What's the derivative of n plus 1? Also 1. and 1 divided by 1 is 1, okay? Now, I should say that we're technically cheating when we do that, because what does it mean to talk about the derivative when I've defined a function that only exists at whole numbers? Well, I can't really do that.
And that would be like a continuous.
Yeah, it's not a continuous thing, okay? And to be differentiable, you first must be continuous, okay? So what I actually am doing there is I'm saying, okay, this function n over n plus 1, I can think of it as being dots on a continuous graph x over x plus 1. The limit of x over x plus 1 is 1 by L'Hopital's rule. And so what should the limit of this thing be? Probably the same thing, right? But I am actually kind of sweeping a detail under the rug there in that process. Okay. Um, and that this will matter for one problem that we'll do in a little bit. Okay. Okay. So what's the lingo that we want to use here? Okay. So suppose that this limit exists and it's some finite number L. Well, then what should we say? We say that that sequence converges to whatever that number is. So for the previous problem we were looking at, it converged, yes, to 1. And it could converge to any other number if I had changed the sequence up. Okay, so if it goes to a specific number, it converges. What else could happen? Um, well, the limit could also fail to exist, right?
Oh,
Right? Okay, so then what would we say? Yeah, we'd say diverges. Okay. Now let me say it this way. It's also possible that we could have an infinite limit if something blows up or goes to negative infinity. Okay. Now, to be clear, if the limit is infinity or minus infinity, does the sequence converge or diverge? It still diverges. It's just we're able to be a little bit more specific as to how or why it diverges. And the reason is that infinity or minus infinity, those are not numbers. Okay, so it only converges if it goes to a finite value. Okay, all right. So in the our previous example, the n over n plus 1, this thing converges, and it converges to what? In that case, it was 1. Okay, great. All right, well, what about, let's say, we'll take this next example. What do you think this guy converges to? Well, there's a couple ways to see that. Yeah, Cole.
okay. So since n's they have the same exponent and the denominator is bigger, like the coefficient or whatever, like that.
The base, but yeah,
It's that number is going to get exponentially bigger.
right?
Like this n approaches infinity, the
Okay.
n approaches 0.
Uh-huh.
Something like that.
Mr. Trapp, do you agree?
Yeah.
Okay. All right, so Cole argues that this one goes to 0. Here's an easy way to see why that's the case. Couldn't I write this like that? Yeah, totally, right? Well, what happens if I square 4/5 or cube it or fourth it or so on? It's going to get really small because 4/5 is smaller than 1. Okay, and so what do you guys expect this limit is? Um, this limit is in fact 0. Okay. Um, Now, a really bad way to approach that problem or that question would be L'Hopital's rule. Okay, and the reason is, what's the derivative of 4 to the n? It's 4 to the n times the natural log of 4. And in the bottom, we'd have 5 to the n times the natural log of 5. Well, that's basically the same question as what we started with, right? Okay, so that's not very helpful. Yeah, so L'Hopital's rule is great, but it also can be a train wreck in certain instances. Okay, so this one converges to, in this case, 0. Um, Now, what about if it had been 5 to the n over 4 to the n? So what about if I'd flipped the fraction upside down? Then what? Then it would have approached, Jack, infinity. Okay, and why? Well, 5/4 squared, cubed, etc. gets bigger each time, right? So it would blow up to infinity instead. Okay, good. And then last but not least, so in this case, I had 4 to the n over 5 to the n. What about if the numbers were the same? Well, what's 1 to the n as n goes to infinity? 1, right? Every time. Now you might say that's like the world's silliest sequence because what is that sequence? 1, 1, 1, 1, 1, 1. Guess what that converges to? I know, big shock, right?
42.
42. Yeah, no. 42 over 42. No, 1. Okay. So it converges to 1, but it's kind of the world's most useless sequence because it's a constant. But on the subject, actually, let me take another example. Let's take -1 to the n. All right, so if I start n equals 1, so start with 1, what is this sequence? -1, 1, -1, 1, -1, 1, etc. Okay? Does this converge to anything? Okay, because if you said it converged to 1, well, there's values where it doesn't, right? The uh, odds. And if you say it converges to -1, well, it doesn't do that either. Uh, could we say it converged to 0? No, not really. I mean, you could sort of say, well, what's halfway between 1 and -1?
Oh, 0.
Right. Okay. So maybe it converges there. It doesn't. Okay. Now the book actually gives a very firm definition of convergence, and let me just write down what it is. Um, and this will sort of explain why this particular situation is not convergent. Okay. All right. So, um, oops. Ah, oops. I need to scoot that over. Okay, you guys have probably never seen a definition like this before. And if you have, color me impressed. Okay, so what is the symbol after for any? what is this symbol right here? Yeah, it's epsilon. It's a Greek letter. You can also write it like that. Um, two variations on the script, but okay. So what does this mean? This definition. All right. So let me take let me take my sequence that converged that I had a minute ago. Cole, pick a value for epsilon. It has to be positive. It can be as small as you want. 8. That's a very big number. Okay, that's also still big. Choose something less than 1. Yeah. 1/4. Okay. Yeah. Yeah, exactly. So next up, you guys can, huh? Oh yeah, and whatever your Twitch name is, so that everybody can like follow you and we can raid your channel later. Um, yeah. Uh, so it sort of hit me the other day. There is no official Wabash College Twitch account. Okay, I like that. Yes, let's make an unofficial one and do shenanigans, right? I mean, I could go and make Wabash College Twitch right now. Yeah, so I think we should have this because then we can be not just affiliate, but we could be a partner and make all kinds of money for the school with our Twitch channel. Yeah, who do you think's idea was that? Yes. The Drurys and Gelman came to me and they're like, "So we want to do this debate watch. How could we do it?" I'm like, "Well, here are your options. Let me run you through all of them." And then they're like, "Okay, Twitch it is." So um, yeah, that's actually why I was sort of realizing that we ought to have an official Wabash College thing. But anyway, okay. So Cole chooses epsilon equals 1/4. All right. So I'm actually going to move over to Mathematica just to give some graphical intuition of this. Um, so let me make sure that the screen actually switches over to the correct thing this time, unlike in this morning's class where it didn't. Yeah, it's because um, if I capture a screen, but I'm also displaying what I'm capturing, then you get inception, right? So that's why that happens. Okay, so let me take here. Well, first off, let me blow up the size. So let me plot. Um, let me just do it, say, from 1 to 10. Okay. All right. Now, this is the continuous version of the sequence that I'm looking at, right? Because I had the sequence is really just this at point values. Okay. And we could draw that discrete version using a list plot. So let me define. Oops. Let me define that, and then I could do, for example, one f of one, um, two f of two, three f of three. Wait a minute, I'm off by a curly brace. Oh, that should be something like this, and then I just get a bunch of dots. Right. Okay. And I could keep doing this, right, if I wanted to, but I'll just, for the sake of cleanliness here, I'll just use the continuous version of it because it's easier to plot. Okay. So here's the question. Cole chose 1/4. Now, what do we claim that the limit of this particular sequence is?
We said 1.
We said it was 1. Okay, that's what we claim. All right, so what I'm going to do is I'm going to change up my plot, and I'm going to graph the function in question, but I'm also going to graph the supposed limit was 1. Cole chose 1/4, right? So I'm going to graph from 3/4 up to 5/4. All right, so I'll graph 3/4 as a horizontal line and 5/4 as a horizontal line. Okay, and so what I get here is I get and while I'm at it, actually, let me graph the number 1. Oops. Okay, so the red line there is my supposed limit. The green and the orange lines are 1/4 unit up and down from that supposed limit. Okay, are we cool with the 3 things I've drawn here, 4 things I've drawn? And then the blue thing is my curve. Okay, all right. The question about convergence is, so we chose epsilon to be 1/4. That's what Cole picked. Is there a value of n so that n bigger than that, the function is always within the green and the orange bands? Okay. All right, let me ask it this way. Does the blue curve eventually get into be between the green and the orange bands? Yes. Okay. Now, let's say that Cole had picked epsilon equals 1/10 billion, right? Would this curve eventually get to be within 1/10 billion of my red line? It would. It just might be way the heck to the right a little bit, right? Okay. So the key here is that, so I can find, in this case, if n is, say, 4 or bigger, am I within my epsilon band? Is the blue curve between the orange and the green things? And it stays there, right? Okay, so let's shrink the value of epsilon. Okay, so for example, let me just say ep equals, let me do 1/10 this time, and then what I'm going to do here is I'm going to do 1 minus ep to 1 plus ep, and that way I don't have to keep typing it.
So if it's always going to be true with this like epsilon thing.
That's the definition of convergence, is that this is true for any epsilon you choose. You just may have to keep going further to the right. Okay, so here, if I shrink my epsilon to 1/10, does the curve eventually get within the orange to green band and stay there? Yeah, it happens like at 10, actually. So if I graph this thing, let me go out to 20. Um, right, it eventually gets inside the green to orange band and it stays there. Okay, no matter how small of an epsilon you pick, that's the definition of convergence here. Okay, and so by the way, how did, in Calc 1, how did you define the limit? Did anybody ever see the limit defined with this epsilons in Calc 1 and deltas? You did that in calculus? Okay, what about you? You did delta epsilon? Wow, that's impressive. I found most calculus classes blow this off because it makes undergraduates' heads explode, much less high school students. Okay, and it's not until real analysis that you get to it. For real. Okay. I don't want to spend too much time on the epsilon definitions, but um, just point being, there is a precise definition of convergence. Okay. The book does mention it for this, and it actually goes through one example. Um, okay. So does that kind of make sense here? And all right. So let me go back to the iPad, and let me also go to here. Let's take one more example. Does anybody happen to recognize what that thing converges to? Just instantly? E. E to the first. Okay, prove it. Well, so I claim that the limit of this thing is E. So I don't know what it is yet, but let me just say it's L. Well, if that's true, well, couldn't I take the log of both sides? And the log is a continuous function, which means the limit of the log is the log of the limit. You can do it in either order. Okay. All right. Well, what's the log of that exponential thing? Oops. Um, this guy here. Okay. Is that good? Right. So when I have an exponent inside a logarithm, he pops out front as a coefficient. Yes. Remember that? Huh? The I don't remember. Oh, right. Yeah, I know. Of all people who should remember that, it's me. But yeah, I fail. Okay, so yes, the law of exponents and logarithms, right, is that I can pop that dude out front. Okay, now the question is, what is this limit? Well, what if n goes to infinity? What is the n part doing? This is going to go to infinity. Okay, what about the logarithm part? What's it going to go to? Well, it's going to go to zero. The inside the logarithm will go to one. Okay, because so what's one over n go to as n goes to infinity? Zero, right? So the entire insides of that logarithm would go to one. One plus zero. Okay, what's the log of one? What's the logarithm of one, Cole? Can't hide from me now. The logarithm of one is zero, right? Oh yeah. I'm sorry, I just didn't hear you. Yeah, the AirPods. No, we're really getting there though. Yeah. Okay. All right. So yeah, the logarithm of one is zero. So this is of the form infinity times zero. Can I use L'Hopital's rule on that? No. Can't use L'Hopital's rule on something that's of the form infinity times zero. But could I rewrite it so that I can do L'Hopital's rule? Yeah, Donovan. Oh, uh, well, okay, sort of. I'm just going to work on the left hand side. Okay, so what eventually is going to happen is we're going to get a number. And so let's say that we get 12, then I'd say, oh, the natural log of L is 12, and then I can solve for L. But yeah, that's what we're up to. Okay. All right, so this is of the form infinity times zero. Can I rewrite this so that L'Hopital's rule applies? This is kind of evil. Isn't that true? But now does L'Hopital's rule apply? It does. Okay. All right, so this is now of the form 0 over 0, and so I can L'Hopital this bad boy. And what do I get? Well, what does L'Hopital's rule say to do? To take the derivative, right? So what's the derivative of 1 over 1 of log of 1 plus 1 over n? It would be 1 plus 1 over n, 1 over that. Well, here, let me make some more space. 1 over 1 plus 1 over n times the derivative of the inside, which would be this, all over that. So what happens? These two terms, this and this, cancel. And I'm just left with that limit, which is what? 1, right? Okay, so let's make sure we're clear that that limit is in fact 1 and that there's no disagreement. Because if there is, then I will just come and shout at you louder until you accept. No,
I disagree.
you disagree. Well, you're wrong. Just my opinion, right? We'll do like every Facebook comment section ever. Right? No, no, where people say something stupid and somebody says, no, that's actually wrong. And they're like, well, it's my opinion. Well, your opinion can be wrong.
Like any social media platform, and it's just like somebody in there just throws in something political for no reason, and then it's just like a huge thread.
Yeah, and then it devolves into,
Yeah, every single place.
yeah. This is why we cannot have nice things. Okay. Okay, so 1 is therefore the value of natural log L. Because we said whatever the limit is, we'll call it L. So if I take log of both sides, then the new limit is natural log of L, and we've just found that natural log of L is equal to 1. And so if the natural log of L is equal to 1, then what's L? It must be e to the first, or just e. Isn't that awesome?
So why would you put 1 over n denominator is equal to 0?
Oh, well, because n's going to infinity, right? So what's if it, so 1 over n goes to 0.
What if it would have just been n in the denominator?
Then it would have been something over infinity, right? So the whole reason I did that was so that I could have it be either 0 over 0 or infinity over infinity, so that I could throw L'Hopital's rule at it. Okay. Okay, so that limit is e. This thing converges. Okay, great. Now, a couple other concepts to, oh, I don't know who this is. So somebody's in the chat, leaky old man butt, but with 1T, not 2. He says, yeah, well, your opinion is wrong. And then now he's no longer in the chat. Oh, no, there he is. He's still there. Okay. No idea who this is, but guess he really wants to learn some calculus. All right, anyway. So, what does it mean for a sequence to be bounded? Well, what do you think it means? Okay. All right, so let me write this out. All right, so A sub n is bounded above it's bounded above if there's a number that the sequence never gets bigger than. Okay. All right. Well, what does it mean to be bounded below? Yeah. That means that there's some number that the sequence is always bigger than. Okay, aka it never gets less than that quantity. Okay, is it possible for a sequence to be bounded above but not below, or vice versa? Totally, right? So you can have a sequence that's bounded above by something but never bounded below. You can also have the opposite situation. Is it possible for a sequence to be both bounded above and bounded below? Yeah, that also can happen. Okay. So, for example, let's take our n over n plus 1 sequence. Was that bounded? It's bounded above. Okay. In this case, it happens to be bounded by 1, but could I also say it was bounded by 10? Yeah. Is the sequence ever get bigger than 10? No. So 10 is a bound, 1 is another bound. Which one's better? 1. The tighter you can get the bound, the more preferable. But, 10 is a bound. Think of this kind of like, you guys remember when we were doing the trapezoid and midpoint and stuff like that, those rules, and we were looking at the error, and we had to look at the K1 or K2 or K4, and we wanted to get an upper bound, but the tighter you could get that upper bound, the better. Same idea. Okay. Okay. So the thing about bounded sequences, okay, is a convergent sequence is always bounded. Now, why does that make sense? Okay, so if the sequence converges, then I claim it has to be bounded. Okay, why does it make sense? Okay, it's approaching a value, right? But let's say it wasn't bounded. Well, then it would contradict the idea of it converging. Okay, so uh, yeah, so maybe think about like how to make that a bit more precise. Convergent sequences, though, are always bounded. Okay, now here's another thing that I wanted to talk about briefly, which is let's take this example. Um, what does the exclamation mark mean? Yeah, it means the factorial function. Okay, so um, what is, say, for example, 5 factorial? How do you compute it? Times 1, right? Okay, so it'd be 5 times 4 times 3 times 2 times 1, right? So you multiply all of the integers starting with whatever you've got down to 1, okay? Now, the reason I mentioned that earlier that things like L'Hopital's rule don't necessarily aren't tools that we can always use is what's the derivative of n factorial? It's a meaningless question, right? Because what would it mean to have 4.5 factorial? It doesn't mean anything, right? Because if the definition of factorial is you multiply integers starting with whatever to go down to 1, well, 4.5 isn't an integer, so that's a meaningless question. There is actually a way that you can fix that, though, with using, how many of you guys have ever heard of the gamma function? Yeah. Oh, yeah. Okay. All right. So anyway, we have to be a little careful with the rules. Um, okay. So the next um, concept I want to define is monotonicity. Oops. Okay. So, well, what do you think increasing means? It never goes down, right? It's always going up. Okay. Now, The precise way to say this in this case is as so, that if you go further down, um, oh, hold on, did I say this backwards? I did say this backwards, hold on, sorry, because I made n bigger than m, so this should, the inequality should be the other way. Okay? Meaning that if you go further on in the sequence, if you're always bigger than somewhere earlier in the sequence, then you're basically always increasing. Or the definition actually has the greater than or equal to, um, which may seem a little silly, but there's good reasons for that. Yeah, so basically, monotonically increasing means that the sequence isn't getting smaller. It only ever stays the same or goes up. Now, on the flip side, could I define monotonically decreasing? Same idea, right? Okay. Now, why we care about that? So um, let's take our sequence that we were starting with. It was this one, right? Is that thing monotonically increasing or decreasing? It's increasing. Okay.
Where's the M?
Oh, M would be an earlier value in the sequence. Okay, so meaning that if I list out the terms of this sequence, what were they? We had what? 1/2, 2/3, 3/4, 4/5, and so on. If I go further down in the sequence, am I getting bigger or smaller? I'm getting bigger. Okay, so M is some earlier index of the sequence, and N would be a later one. Okay, so like let's say that you pick N is 5 and M is 3. Is the fifth term bigger than the third term? Yes, so it's increasing. Okay, all right, so this thing is increasing. You guys would agree. It's also bounded above, as we said a minute ago. So, what do you think is going to happen to a sequence that's bounded above and is always increasing? It's going to approach something, right? Some limit. Now, it may not be the value of that bound. So, for example, if I picked 10 as my bound for n over n plus 1, right, this sequence doesn't converge to 10, but it does converge to something. Okay, so this brings us to a theorem, which is a monotonic sequence that's decreasing and bounded below converges. Or if it's increasing and bounded above, it also converges. Okay, so let's think about why that makes sense. All right, so if I have something that is bounded above, okay, so let's say here's a bound, and I've got a thing, and I never go down, well, I'm going to converge to something because I can never do something silly like this, right? Because that would violate being monotone. Okay. And then on the flip side, if I'm decreasing and bounded below, then what can we say? Yeah, same thing. You also have to converge. Okay. Now you can't mix these. If you're bounded below but increasing, can you say anything? No, not necessarily. Okay. It depends on the function. Well, you can say things, but they might be wrong. Well, it's monotonically increasing but bounded below, but that doesn't get you anything, right? Because I could come up with an example, two examples of things that were monotonically increasing and bounded below, but one converged and the other diverged, right? So that I can't necessarily conclude anything. However, if it's increasing and bounded above, then I can guarantee it converges. Okay, so just depends on what you got. Um, okay, so I guess that's probably a good place to quit here. Huh, though, here's, I guess, a good question. So I had the 2 to the n over n factorial a minute ago. who wins this tug of war, if you will, right? So if I take 2 to the n over n factorial, and I imagine like, well, when n equals 1, what do I have? I have 2 to the first over 1, which is 2. When n equals 2, what do I have? I 2 squared over 2, which happens also to be 2. All right, when n is 3, what would I get? 2 cubed is 8 over 6. I would get 4/3, 8 over 6, right? Uh, so do you think this is going to converge to something? Well, it's not immediately clear, but what happens if I put in like 10? What's 2 to the 10th?
1024.
Yeah, okay. Um, oops. Yeah, from this morning, exactly, right? So, um, all right, so let's take 2 to the 10th. It's this. What is 10 factorial? That's really big. Okay, so what's the fraction, the ratio of those two things? Right, it's that, which is a number is like that. Okay, so who do you think is going to win this tug of war, the 2 to the n or the factorial function? The factorial function is going to just, in the long run, slaughter the exponential.
In terms of getting closer to 1 faster? Or to 0 faster?
To 0, yeah. Well, okay, so actually, let me rephrase. The sequence is the ratio of those two things. Okay, so what I mean by the tug of war here is both 2 to the n and n factorial go to infinity, right? But the n factorial goes to infinity so much faster that the ratio is going to go to 0 because the factorial was what I put in the bottom.
Mm-hmm.
Okay. All right, we should quit there. Reminder, Monday, of course, we've got our fun and exciting um, fluency assessment, celebration of learning. Um, and so we won't be on Twitch. And those of you guys who are online, I will email you your assessment basically right at 9 o'clock or so Monday morning, and then you can turn it in on Canvas. All right, so I'll see you guys on Monday or Wednesday. Bye.